Jnanam paramam dheyam. Knowledge is supreme.
Welcome to week 3 of this course. In the previous week we looked at the simplest of the dynamical systems, which were first order systems. In this week we will look at second order systems as well as higher order systems, which we would be approximating as first order plus date time, and also we will look at some additional different types of dynamics which come under the umbrella of numerator dynamics. So we will start with the second order systems. So at the end of this part of the lecture, the objectives are that you should be able to identify as well as classify a second order dynamical system. For the second order systems, there are three parameters. One is the process gain, natural period of oscillation, and the damping coefficient. So you should be able to tell the significance of each of those for the system at hand. And lastly, you should be able to predict how a second order system responds to a step change. So let us start with what characterizes a second order dynamical system. The second order dynamical system is a system where the output of that system is given by a second order ordinary differential equation. So the general form of that will be A2 d2y over dt square plus A1 dy by dt plus A0y is equal to b times u, where y is my output in deviation form and u is my input in deviation form. And obviously the condition is that A2 should not be equal to 0, because if A2 is equal to 0, what we have left with is the first order differential equation. So this will be a first order system, and then all these other constants are there. So we will typically write this in a form which was very similar to what we did for a first order system, is that we divide all over by A0, so that we want the coefficient multiplying y to be 1. And then the way we represent these, we represent this as a square of a parameter tau, tau square. But mind you, this tau, even though we are using the same symbol as time constant for a first order process, most of the time this tau is different from the tau which we had used for first order system in terms of significance. Only in one particular case it has the same significance as that of first order time constant. Its name is also different. It's called as the natural period of oscillation. Why it is called that way, we will look at it when we look at the response of this system. But for all other purposes, the symbol is the same, but the meaning is different. This A1 over A0 will represent it as twice zeta tau. So the tau is same as this, and we have a new variable zeta, which is known as the damping coefficient, and this is same as the earlier nomenclature of gain Kp. So a standard form of second order dynamical system is that if we just write it down again, it will be tau square d2y by dt square plus twice zeta tau dy by dt plus y is equal to Kp times u. So this is the standard form for a second order dynamical system, where tau is known as natural period of oscillation, zeta is known as damping coefficient, and Kp is known as process gain. So, like the first order systems, we will also take a Laplace transform that will give us the transfer function for the second order process. If we take the Laplace of this particular equation and write it into a transfer function notation, so what we get is the transfer function g of s, which is ys over us. What you get as Kp over tau square s square plus twice zeta tau s plus 1. So, it is second order in terms of, it is a quadratic in terms of the Laplace variable s. So, let us now look at what are the different cases when we get a second order dynamical system. If we try to recall what we had done for the first order process, what we had was that first order process is the process which is characterized by its ability to store material or energy. Similarly, we will try to see what are the different physical phenomena which are going to give rise to a second order dynamical system. As it turns out, there are three ways to get a second order dynamical system. We will cover them one by one. So, the first way ways to get a second order dynamical system. So, the first one is a series connection of two first order processes. Or systems. So, now keep in mind this is a series connection. We had looked at a few examples in the previous week where there was a parallel connection of first order capacities. Whenever there is a parallel connection, then the overall order of the system remains the same. Now, here we are talking about a series connection. The output of one feeds as the input of the other. So, when we have such kind of a arrangement which is also very common in our chemical industry, what we get is a second order system. So, it is like addition of two first order processes in series is going to give us a second order system. We will consider an example which you might have seen in your reaction engineering course, which is CSTRs in series. So, CSTR is a first order dynamical system. We will see that in a minute. So, let us see what is this particular system. So, we have one CSTR. Let us say the input coming in is CAI, the volume is V1. Everywhere the reaction which we are going to consider is a simple reaction A going to B, and the output of this is going to be CA1, and what we have is this output goes to a second CSTR which has volume of V2, and what you get out is the final product which is CA2. So, now what we are interested in is what is the effect of variations in inlet composition on the final variations on the final product purity. So, you can see that when we change a CAI, it is going to have some impact on CA2. So, we will try to quantify that, and as we are in the topic of second order dynamical systems, what I should be able to impress upon you is that this variation indeed follows second order dynamics. So, we will try to formulate a process model for this particular system. So, we will start with material balance. Now, for simplicity, here I will assume that volume of this CSTR remains constant. We will not consider variations coming from inlet flow. these can be considered, and you can still show that it is the system still follows second order dynamics, but just for the constraint of time and for just proof of concept, we will assume that volume remains constant and variations are in CAI. These are the variations we are going to consider. So, what we will be writing is a component mole balance. So, the total material coming in would be F, which is the total flow rate, times CAI. This is for CSTR1. What the material going out of this system would be F times CA1. The rate of consumption would be K times CA times V, and lastly there is no rate of generation. So, this has to be equal to the rate of change of content of that particular species, which is V times CAI, CA1. So, if we try to simplify this, what we would get, this is V1, what we would get is d CA1 by dt is equal to F over V1 CAI minus CA1 minus K CA1. So, this also has to be 1. So, you can see that this is a first order process between CAI and CA1. So, our first CSTR is a first order process between its input concentration and output concentration. So, similarly for CSTR2, which is exactly the same except that it has a different volume, we can write that CA2 dCA2 by dt is equal to F over V2 CA. Now, here the input for the second CSTR is CA1 minus CA2 minus K CA2. So, this is our equation 1 and this is our equation 2. So, we have two first order processes which are connected together through this term CA1, because you can see that whenever there is a change in inlet composition which is CAI, it is not going to directly affect CA2, because if you look at the equation 2, you will see that there is no term for CAI. So, CAI is not going to directly affect the concentration of second CSTR. Whenever you change CAI, it is going to first change CA1. So, it is going to affect the first tank directly. It will cause changes in CA1, and those changes in CA1 are now going to drive the changes in CA2. So, that is how it is a series connection between two first order capacities. So, let us now try to formulate the final transfer function between CAI and CA2. So, for that we will first have to write these equations in deviation forms. So, we will be writing the equations at steady state. So, at steady state what we have is for first CSTR, it is 0 is F over CA1 CAI SS minus CA1 SS minus K CA1 SS. And similarly for second CSTR, we will have F over V2 CA1 SS minus CA2 SS minus K CA2 SS. So, if we do 1 minus 3 and 2 minus 4, we will get the deviation form of these equations, which looks like d we'll call it as equation 5, and for the second CSTR we will have now. At this point there are two ways to show that this particular system between CAI and CA2 is a second order dynamical system. One way is that we'll eliminate CA1 from these two equations. The way you can do that is by differentiating equation 5, differentiating equation 6, which will give me second order derivative with respect to CA2, and it will have first order derivative with respect to CA1, and then that dCA1 over dt will substitute from 5, and eventually we will also have to write CA1 in terms of that from equation 5, equation 6, and eventually what we can get is the second order term in terms of CA2 will have some contribution coming from CAI. Now, as it turns out, it becomes very lengthy. What we will use is a simpler method of getting a transfer function, which is by taking Laplace of both the both the equations, and then eliminating CA1 Laplace from that. So, we will take a Laplace transform of these two equations. So, Laplace transform, and as we are working with deviation variables, we do not have to worry about the initial condition. So, we will have SCA1 Laplace is equal to f over V1 CAI S minus CA1 S minus K CA1 S, which we can write as CA1 S over CAI S. So, we will write a transfer function for the first CSTR, which will come out to be f over V1 divided by S plus f over V1 plus K. Let us call it equation 7. So, this is the transfer function between changes in the inlet concentration to changes in the first CSTR concentration. So, similarly for the second CSTR, we will get, if you do the same analogy, the equations are similar. So, we can simply write this other transfer function by comparing it with equation 7, which gives us so now we have two transfer functions, one between CAI and CA1, and the other one is between CA1 and CA2, and we need what we need is CA2 over CAI. So, we can simply multiply equation 7 and 8, and then the CA1S will get cancelled out from numerator and denominator. So, we do 7 times 8. So, we are going to get and you can see that these two terms are going to cancel, and the final transfer function we get which is a polynomial, a quadratic polynomial in S. So, it is a second order dynamical system. So, here I am not trying to put it into the general form of tau square S square plus twice zeta tau S plus 1, because for that I need to have this coefficient to be 1, which would require me to divide take this particular f over v1 plus k common from this side and f over v2 plus k common from this side, and then go to the top, and accordingly your gain will also have that multiplication factor. But the point is, what you are seeing is there is a S square term, so it is going to be a second order dynamical system. So, what we have seen is that when we connect two first order capacities, which in this case was these two first order tanks, what we got is a series connection, what we got is a second order dynamical system. Now, there are two ways in which these series connections can be done. This particular type of a series connection is known as a non-interacting type connection, because what we are going to see is the direction of effect of the disturbance is one way. So, when we have any changes in the reactor 1, they are going to get translated to reactor 2. However, if there are some changes in reactor 2, they are not gonna get back propagated to 1. So, the direction of interaction is only in one direction. The second tank does not interact with the first one. That is why this type of connection is also known as non-interacting series connection. You may be wondering, can we have a interacting series connection between these two tanks? Yes, we can. Let us say there was some sort of a recycle going from this particular stream back to the reactor. In that case, any variations in reactor 2 would also affect reactor 1, and these kind of interconnections, series connection will be called as interacting series connection between two first order systems. So, these series connections can be interacting or non-interacting, and if you refer to textbooks, you will see that typically when we have interacting systems, then the systems are slower compared to non-interacting systems. So, that was one way of getting a second order dynamical system. Let us look at the second way of getting a second order dynamical system, which is a first order system under feedback control. So, what we are seeing is to get a second order system, we actually have to start with a first order system. That is why in the last week I had said that first order systems are the primary or the basic fundamental type of dynamical system. In order to study a second order, get a second order system, we will start with a first order system. So, here we are going to look at a first order system under feedback control. In the first week we had looked at what is a feedback control. Just to recap, feedback control is a control mechanism wherein you measure the controlled variable, and then looking at the deviation of that controlled variable from its desired value, you change the manipulated variable. So, you take a feedback from the system and make a change to the manipulated variable. So, here the system which we are going to consider is the simple surge tank which we have been seeing as a first order system. So, the example we are going to consider is surge tank under a specific type of feedback control, which is integral control. So, we will take a short break here, and after that we will try to analyze this type of system. Thank you.